like Algebra 1 questions paired with pre-calculus functions, really. When we talk about evaluating functions, function notations, I give you a function f of x, and then I say find f of pi over 4. What am I asking you to do?
Plug in pi over 4 for x.
Thank you. Plug in a pi over 4 for x. Not a trick question, just a nice little reminder of what that means. I can change the letters, but it doesn't change the concept. H of s equals a square root, blah, blah, blah. H of 6, we go plug in a 6 for every single s. Not difficult. As we started to learn more functions, we talked about square root functions, we talked about trig functions, we talked about reciprocal functions last year. As we start learning new functions or learning new operations, we can start graphing their functions. So I gave you something like this on worksheet, and I think it was on worksheet 9 on Friday. What if your function looked like this? We're going to work with this function quite a bit today. G of x equals the integral from 1 to x of, not a typo, 2t plus 3 dt. It's a function. There's variables. In fact, there's a couple of variables in it. We'll explain that. But the question is find g of 4. What do they want you to do?
4 for x.
Plug in a 4 for x, right? G of x, g of 4. So there's a lot of variables there, but they want you to go plug in a 4 for x only. And now we have something that we can handle. How do we do this? We've been doing this for over a week now. You can do it 2 ways, really. You could draw this because it's a line and then go find the area, net area from 1 to 4. Or now we know we have a better way to do that. Take the antiderivative and then evaluate it from 1 to 4, right? So plugging in a 4, 16 plus 12 minus 1 plus 3. Okay, so it's just, now we're saying, hey, we've got this new operation. We've got this integral that tells us what to do. Well, if it's an operation, we can certainly put it in a function just like we would a square root or a trig function. Okay. All right. So just a quick little warm up, just a reminder. So again, the reason we have to use 2 variables here is, and don't, again, we're not writing any of this down anyways, but if they would not have used 2 different variables, if we use that idea of, like Ansley said, that tells us to go plug a 4 in for x. Well, if we plug a 4 in for x, we'd plug 1 in here, we'd plug a 4 in here. What would it even mean to have d4? Right? So the idea is we have to temporarily change the variable of the function, the integrand, so that we're saying this is the variable we're referring to. Whether we're talking about the line y equals 2x plus 3 or y equals 2t plus 3 or y equals 2 theta plus, they're all the same graph. We're just changing the name of the x-axis. So this is a temporary change so that we don't confuse these. And we're saying we're just changing the upper bound. A lot of what I said is already written on your first slide, so that's my fault. But let's go ahead and take a look. There's a lot of words here. Most of it is what we just said, just phrased differently. Let's get to this in a moment. This is our goal today, is to talk about the fundamental theorem of calculus part 1. I know you've been anxiously awaiting part 1 because we've learned part 2 last week. But the idea is that the definite integral can now be found in functions because it's an operation. Why not? What we've been looking at in the last week or so are definite integrals where the bounds were constants, right? The bounds were from like 1 to 7 or -1 to 3, which meant that the integral itself represented a defined area, and so the answer was just a number, right? Well, what we may now start seeing is that the variable x, it doesn't have to be an x, it could be any letter as we know, but the variable x may be started to use as a limit of integration, meaning that now this integral is part of a function, right? The upper bound is changing. We already said this, but so that we don't have any confusion, we'll use a temporary variable of integration, which is what the variables inside the integral. Typically it's t, but it could be anything. It could be a u, it could be a theta, it could be anything. But that's just so that we don't confuse the bound variable with just the graph of the function. Okay. So today we're going to be talking about this concept of an integral inside a function. So these functions have names, just like we call trig functions. We call I don't know, we have names for all, quadratic functions. This, when you have an integral of a function, it's called an accumulation function. Why? Well, because every time you start changing that upper bound, and I'll explain, we're talking about accumulating area. Whether the area is positive or negative in value, that's, depending on the function. So let's think about this for a second. Let's say I said find g of 2, or g of 4, or g of 10. I just picked numbers. It doesn't matter. It's kind of what I asked you to do in homework last night, maybe with a different function. I forget what the function was. If I said go find g of 2, you, just like we said, you'd put a 2 up here. And I'm not actually going to do the math, but it'd be saying find the net area under the line, and I'm not going to write that, I'm just going to say under the line, between 1 and 2. This is horribly written math, I get that. I'm trying to make it not too wordy. The net area under the line, y equals 2x plus 3 from 1 to 2. Well, if I said go find g of 4, well, the only thing that's going to change is that we're not going from 1 to 2, we're going from 1 to 4. So it'd be the net area under the same line, but this time from 1 to 4. We're starting in the same place, but instead of going from 1 to 2, we're going from 1 to 4. We're accumulating more of that area under the graph. Same thing with g of 10. It'd be the net area under the line from 1 to 10. So the y values of this function represent accumulated areas under the original line. Okay. Now, these graphs, and we're not going to talk about the graphs today, but the idea is when we learn a new type of function, we typically say, what does the parent graph look like? Well, these don't have one graph, and that's because it will depend on what's inside here, because it's an operation, right? So it's not like I'm going to just say, hey, all of these graphs look like this, and then we're going to talk about moving them up, down, side to side. Because they're all so different, we're not going to memorize anything, but if we wanted to talk about those graphs, it would be helpful if we could find their derivatives, right? Because we learned in Unit 4 that if you can find the first derivative of a function, you can find out when the graph is increasing, decreasing. You can find maxes and mins. We can go to the second derivative and find intervals of concavity and inflection points. So not today. We're not graphing anything today. That's not our goal today. But if you had an accumulation function and you wanted information about it, we could get so much information from the derivatives. Maybe we should first learn how to take the derivative of these types of functions. That's our goal today. So kind of introduce this new function. We're going to talk about what is its derivative. So I'm going to highlight it because I don't think it stands out very much. This is our goal. How do we find the derivative of a function that has an integral in it? Okay, that's our big goal. All right, well, let's start with what we've just been looking at. So here's the thing. I've got this function g of x, and I'm saying, how do we find its derivative? We don't know. So maybe we clean it up, right? Even last week when I said, how do you integrate this? You'd say, well, I don't know, but I can algebraically make it look different. Same thing. Let's algebraically make this look different. How do we evaluate integrals in general?
Find the antiderivative.
Find the antiderivative. Oh, well, let's do that. So I'm not answering my highlighted question. I'm just cleaning it up. If I take the antiderivative, I get 2t squared divided by 2, right? I add 1 to the exponent, divide by the new exponent, plus 3t. And we'll evaluate that from 1 to x. Because at this point, it's the only thing we know how to do. If the function has an integral in it, let's evaluate the integral, even though the integral has a variable. We'll come back to that. So here we go. We've got, we plug in the upper bound, and I get x squared plus 3x. This is our rule from last week. Minus, and then we're going to go plug in the lower bound. And when I plug in the lower bound, I get 1 plus 3, which is, well, I'll just call it 4. I guess I don't need parentheses there, but that's okay. So here's what we just said. We've just said g of x is this, which is what they gave us, but it's really x squared plus 3x minus 4. That was a a really, really fancy way to write the equation of a quadratic, wasn't it? But it's what it is, right? So they gave us this function. We cleaned it up and realized this is a lot easier than we first thought. What are we trying to do? We're trying to take the derivative of g. Here's g in its nicer form. So g prime of x equals, well, let's just take the derivative of g. And we get 2x plus 3. Some of you are going, wait, what just happened there? Let's just, hold on a second. They gave us this wild function, and we want the derivative. So we cleaned it up to make it look like this, so that we could take its derivative. And some of you are going, huh, I don't feel like we did anything. I agree with you. Because what did we actually just do? This symbol tells us to take the antiderivative, but then we took the derivative. Well, that's like saying, hey, take 2 steps forward, and then you know what? Take 2 steps right back. Agreed? Like, you don't go anywhere. Why move? They asked us to take the antiderivative of the line 2t plus 3, and then take the derivative, and we got the line 2x plus 3. That's not a coincidence. We took an antiderivative so we could turn around and take a derivative. We shouldn't change much about the function. Let's do another one. I didn't change much. Look at the only thing, so I've changed the name of it. The only difference is that the lower bound is not a 1 anymore, it's a -6. Let's see what that changes for us. I know I didn't leave us a whole lot of room here, so let me maybe do something like that. That's just me, I'm a little crowded here. If we're being asked to find the derivative of this function, let's clean it up first, just like we did up top. So again, I'm going to take the antiderivative, which this time I'm just going to use the cleaned up version, t squared plus 3t. And I want to evaluate it from -6 to x. So I plug in my upper bound and I get x squared plus 3x. And when I plug in a lower bound, I get 36 minus 18. Oh, all right. So h of x, as I simplify, equals x squared plus 3x minus 18. It's a different function, isn't it? The one up here, g of x, was x squared plus 3x minus 4. This pink one, this h of x, is still a parabola that's been moved down. All right. What's that going to change about its derivative? Not a thing, right? Because what's the derivative of a constant? 0. So again, we started with an integral. Integral means take the antiderivative, but then we turned around and took the derivative. So we got the exact same function. Different letter, I get that, but it doesn't change the shape of the graph. So essentially we got the same graph. What changed was the lower bound, but now we're finding that even though the lower bound changes the function itself, it doesn't change the derivative, does it? Okay. We're starting to see a pattern. We're starting to ask ourselves, like, wait a second, why are we doing all this work? Right? We're not really getting anywhere. We're not changing anything. Well, yes, I agree. Let's take a look at this third one before we really make a ruling here, if you will. Maybe I should do this again. Okay. Again, I know. Sorry about the space. New function, kind of. The integrand is not any different. The bounds are different. What I noticed this time is that the x is on the bottom. Is that going to change anything? I don't know. Let's find out. Let's just kind of just go right after here. So same idea. Let's clean up the function they gave us. Take the antiderivative, and we're going to plug in the bounds. We're going to plug in the 4 first to get 16 plus 12, 28, whatever you want to call it, minus, and then we plug in the x to get x squared plus 3x. Make sure you're using parentheses. You've noticed I've been using them. So we can clean this up, and we can clean it up obviously a lot of ways. I see a 28 here, and then I can distribute the negative if I want. I'm actually not going to on purpose, but you can. It doesn't matter. I'm not going to, and we'll see why in a second. So I have 28 minus x squared plus 3x. Okay. That's my function. Now it's different than the first two, isn't it? It's close, but what's different about it? These two were x squared. X squared. What's this one?
Negative.
A negative x squared. So the function is slightly different. It's not an opening up parallel, now it's opening down. All right, well, let's take the derivative. K prime of x equals 28 is gone. The negative stays there, right? It's a constant multiple rule. And the derivative of the inside of that second piece is 2x plus 3. I mean, it's so close, right? 2x plus 3 or 2t plus 3 turned into 2x plus 3. Where'd the negative come from? Flipping of the bounds. This was the first of the three where the variable was in the lower bound. So it's like, oh, yeah, it was a little different, but we learned last week if you think the bounds are in the wrong order, by the way, there's never a wrong order, but if you feel like the bounds need switched, you can switch them. It's going to just change the sign of your answer, and there it is. So we feel like, and I think some of you already saw it by the first one, but we feel like we've seen this pattern. As long as your variable is in the upper bound, and if it's not, we can switch it. When you are asked to take the derivative of an integral, the function doesn't change. The integral goes away because that's what said take the antiderivative. We're left with what's in the integrand, the function we were integrating. So let's take a guess. Let's not do this one the long way. Let's take a guess. I'm saying capital F of x equals the integral from 0 to x of cosine of 2t dt. And I would like us to find the derivative of this function. I went ahead and left it as capital F prime. That way we just see for sure. Yes, it's the derivative of capital F. You could call it little f, but we'll leave it alone. Based on what we've been doing, what do we think the answer should be?
Cosine of 2x.
Cosine of 2x. Because again, the function that's inside is the cosine of 2t. They're asking us to take the antiderivative, but then here it says take the derivative. So it's like, well, that's silly. So let's not do all the work. The only thing that changes is that the t's go back to x's. That's what we saw on that first slide. And that's exactly what it would be. We could do that by hand. We could do it the long way, and we get the same thing. It's not even a shortcut, right? Because some of you are going, oh yeah, I see the pattern, I see the shortcut. It's not a shortcut, it's the fundamental theorem of calculus, part 1. The reason I teach part 1 second is because I use part 2 to help us see part 1. It doesn't matter. It's a really big deal, and it says, formally written, if you want the derivative of an integral function, so to take the derivative of the integral from a to x, who cares what a is, of a function f of t dt, the only thing we really felt like we were doing is just changing all the t's to x's. Why does that work? Because the derivative of an antiderivative wipes each other. They undo each other. They're inverse operations. So we should be left with the function f. We just happen to change the letter name back to x. That's easy. I'm telling you, we're going to do these. There's going to be no work to do. Right? How much work did we do up here? None. We didn't actually take any derivatives. We didn't physically do any antiderivatives. That's the big deal. The fundamental theorem part 1 says to take the derivative of an integral, you're just going to take that upper bound and go plug it in. That's it. Easy. So let's do a few examples. Now I made the functions a lot more difficult to kind of prove that you can't do some of these the long way. You shouldn't have to. Now I changed the letters. Don't let that bother you. Maybe I got, ahead of ourselves a little bit. G of theta equals the integral from 1/2 to theta of this lovely function in terms of u du. I mean, okay, I could have used some x's in there, maybe I got a little ahead. They want the derivative. The derivative of an integral says you're just going to take what's inside the integral, which is the square root of e to the blank plus the sign of blank. They were used. What are we going to change them to?
Theta.
Thetas. That's our answer. That's the derivative of the function they gave us. Do I touch the 1/2, that lower bound? Not at all. Because look back here. The rule said it doesn't matter what the lower bound is. That a is nowhere in here. We don't use the lower bound. We don't use that constant because the derivative of a constant would be 0. These are easy. It's going to be the easiest math we've done all year. Some of you are still waiting for like the catch, right? That's, I mean, when they're just, I want to say there's a slight catch, a slight change, but we'll address that in a minute. Second question, phrased differently, still the same thing though. D dx, take the derivative of the integral. That's like saying take the derivative of the antiderivative. Take 2 steps forward, take 2 steps back. Nothing's going to change. One thing's going to change. The function is t squared minus 2t plus 3. But I'm not going to use t's, I'm going to use x's. So, and I could kind of write it this way. The rule says you're just going to take every t and change it to x. We're going to love these, right? I think. How about the third one here? Y equals the integral from x to 10 of this lovely function. Find y prime. They're asking for us to take the derivative. One difference here is that my x is in the bottom. So whether we do it in our heads or we write it on paper, the first thing we should do is to switch the bounds so the x is in the top, which means we need to throw a negative out in front. This is not my answer. This is just me rewriting my function. So the fundamental theorem says for the rule to work, the variable has to be in the top. Easy switch. Switch the bounds, throw a -1 out in front. Now we get to use our so-called shortcut. I hate calling it a shortcut because it's not. It's a rule. It's a theorem, right? But the theorem says you're going to replace all of those t's with x's. That's it. So we've got, don't forget the negative, right? The constant multiple rule says we need the negative. But then in the top we have an x squared, and in the bottom we have an x squared plus 1. That's my derivative. Now, I will say, because there's so little mathematics in here, because we feel like we're not actually doing anything, we tend to lose sight of what we're finding. And a lot of folks just think, oh, I'm just changing the way it looks. No. Remember, this is the function. This is its derivative. We are taking the derivative. We just feel like because we're missing some steps, we feel like because we're not doing anything that we're not actually changing anything. But we are. We're finding the first derivative. And by the way, now that this is the first derivative, if we needed the second derivative, now it's very straightforward for us. Now it's taken us back to, months ago. Easy, yeah? It's going to be one of the easiest homework assignments I give you, honestly. All right, let's talk about a slight, small catch, if you will. What about this one? And I picked an easier function so that we could do it the long way, just in case we feel uncomfortable. But it's the same idea. It's still a function that has an integral in it. And that integral has a variable in the upper bound. It's just not an x, it's a 3x. So we're going, I wonder if the rule still works. So if this is my function, what is the derivative? And we're going, I don't know. The rule says make sure the variable's in the upper bound, which it is, and just go plug it in. And so we're wondering if it still works. And I think we should kind of wonder because we have a change. Everything we've been doing up until this point was just a 1x, 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 1x. That's why I put a question mark there. I'm just saying, I don't know, I think. It's what the rule said to do. Well, if we're not sure, let's do it the long way. Let's just check. So maybe we just clean up the function. What's the antiderivative of sine theta? Close?
Negative cosine.
Negative cosine. The derivative of sine is cosine. So the antiderivative is negative cosine of theta. And we want to evaluate that from 0 to 3x. All right, so we've got a negative cosine of 3x minus a negative cosine of 0. Which means g of x equals negative cosine of 3x plus 1. So I picked one that we could do the long way again. So g of x looked like this, which was messy. We cleaned it up, so it looks, well, this is nice, right? Let's take the derivative, because that's what we're being asked to do, right? Is that g prime of x equals. So we start out here. The derivative of negative cosine is?
Positive sine.
Positive sine. I know, our head's going to go crazy. We'll write it down. The derivative of negative cosine is negative sine of 3x, right? The inside stays the same. The chain rule says multiply that by 3. Did I write negative sine? And I meant to. The derivative of negative cosine is positive sine. I don't know what I said and what I wrote. I don't know. Did I say one thing and write another?
Yeah, you said positive.
And okay, so I didn't think I said it wrong. That's my fault. Okay. I said it right though? That's good. The derivative of negative cosine is positive sine. I think I wrote a negative there. Times 3. We thought, based on the rule we wrote down, the answer should just be the sine of 3x. But when we did it the long way, we have an extra 3. Why? Because of the chain rule. Right? We saw, as we said, the chain rule says multiply by 3. But why do we have the chain rule? Because we plugged this in to our function. So it was just the sine of theta, but as soon as we plugged in something other than x, it was a 3x, that forced us to use the chain rule when we were taking the derivative. That's okay. We just need to make a slight adjustment to our rule. The last time we wrote the rule, it said from a to x. But what if it's not an x up there? What if it's a 3x? What if it's a negative x? What if it's an e to the x? Writing it this way is now more complete. And we're going to say it doesn't matter what's up there. It could be any function of x, even if it's as simple as 3x. But the rule says you're going to do the same idea. To take the derivative, you're still going to make sure the variable's in the top. We're going to go plug it in, so we get g of f of x. But then we're going to need to multiply by the derivative of that upper bound. So it's the same rule. We're still going to use a shortcut. But if that upper bound is anything other than a single x, we're going to want to make sure we multiply by that derivative of whatever that was up there, that upper bound. It's an easy fix. So let's take a look at a few examples. Start with this one. d dx, take the derivative of the integral from 4x squared to 3, and then my function is 2u to the negative 1 du. Well, I think we see a couple things. If you don't like the negative exponent, then deal with that and rewrite it, and that's up to you. Basically, they're saying the function, I'm getting rid of the derivative, so I'm going to try to use some equal signs. They're saying the function is the integral from 4x squared to 3. I'm going to flip that. So I threw a negative out in front. This is not my answer. I'm just rewriting it for my own sake. A lot of you will do this without rewriting it, and that's okay. So I'm going to switch the bounds, throw a negative in front. You can leave that as 2u to the negative first, or if you think it's nicer to write it as 2 over, you do whatever you need to do. I just honestly didn't like the negative exponent, but that's maybe an issue I have. I haven't done what they've asked me to do yet. They're asking me to take the derivative of this. So they're asking me to find dy dx, or y prime, whatever you want to call it. Dy dx equals, the negative stays out in front, constant multiple rule. The rule says take your upper bound, the variable upper bound, and go plug it in. So I have 2 over 4x squared. The chain rule says multiply by, and that's why I like doing this. I like circling this. The chain rule says multiply by the derivative, which is 8x. And that's it. No, we can clean it up. Actually, we can clean it up like a lot. And what are we left with? What, 4 over x? 4 over, that's an easy function, right? Clean this up. The 8, the 2, 16 divided by 4 is 4. Yeah, I'm left with negative 4 over x. That's a great derivative. We can do a lot with that. We can say, when is it positive? When is it negative? When does it not exist? We can take the second derivative. So again, first thing, make sure the variable's in the upper bound. Easy. Put a negative out in front. Plug that upper bound in, and then multiply by the derivative of the upper bound. Let's take a look at the next one. I'm just changing what I'm asking here, giving us a new function. So h of x equals this lovely thing here. I know they're messy. So there's our function. Find h prime of 1. The question itself is not new. Since back in, September, I've been saying find h prime of 0, h prime of 5, h prime. What are we going to do first? You want to find h prime of 1.
What h prime of x?
We're going to find the derivative. We're going to find h prime of x. And then what? Plug in a 1. So it's just, now it's multi-step. Instead of just finding the derivative, this is old, we've been doing this before. They want us to find the derivative at a point. They're asking us to find the slope of this function at x equals 1. And I should fix that. I didn't mean for this to have the same upper bound as the one we just did a couple, 2 ago, so that, I could add a little variety here. All right, so the first we need is h prime of x. To find the derivative of the integral, it just says make sure your variable's in the upper bound, which it is, and go plug it in for every t. All right, so I have the square root of 4 blank squared plus e to the blank. Right, the integral's gone. So I'm going to go plug in a 3x for every t. The chain rule says multiply that by the derivative of the upper bound, which is 3 again. This is my derivative. I know it doesn't look great. We can clean it up, but this is h prime of x. We didn't really do a whole lot of math. I never really, besides this little chain rule thing, I never actually took a derivative. I never took an antiderivative, right? Can't get any easier than this. So if you want to clean it up, great, but at the very least, we need to go plug in our 1. And so I can move the 3 out in front. In fact, I probably should do that. So h prime of 1 equals 3 times the square root of. If I plug in a 1 in here, I get 9 times 4 is 36 plus e cubed. Which I know, can't do anything with it. It's not the nicest looking answer we've seen. But no one says we need nice answers. We just leave it alone. Okay. Good. I think we have a few minutes left, don't we? We can talk about that last one. All right, let's take a look. Excited. That's our final answer. I guess my square root was a little long, but there it is. Oh gosh, it's been a while since we've done or seen this phrase. Write the equation of the normal line to this curve. So here's my function, my y equals when x equals -1. Right, the equation of the normal line. Let's stop for a second. Liam, if I want to write the equation of any line, what do we need? We need some variables like x's and y's. What information would help us write the line? Think algebra 1. We could use the x and y intercepts, right? Those are examples of points. What else? Slope. I think it's very basic information we need. At the very least, we need a point and a slope. And we've said you can get that slope. If you have 2 points, great. But at the very least, to write the equation of a line, we need a point and we need a slope. This is how we started every single one of these problems. Now, we have to be careful because they don't want the tangent line. They said they want the slope of the normal line. How's that any different? What do we typically find? Slope of the tangent. And slope of the tangent comes from the derivative, and then we'll use the opposite reciprocal. So when we were doing these before, it's been a while, my notes to myself, because sometimes we get so wrapped up in taking the derivative, we forget that they asked us for a slight change. So I would do something like this. We're going to find the point. By the way, they already gave us half the point. And then they want us to find the slope of the normal. Well, the easier thing to do first would be to find the slope of the tangent. Okay, well, let's finish the point. How do we find the y value of the point? We plug in the x into here, don't we? Y equals 2 times -1 minus the integral from 1 to -1 squared of t cubed plus 7t dt. If you want to find the y value, you go to the function and you plug in the x. And so I did that in the 2 places they had an x. I know it looks like it's a mess, but gosh, clean it up a bit. And we have -2 minus the integral from 1 to 1. What's the integral from 1 to 1? 0. So we really have a y value of -2. It looked like it was going to take us forever, but it didn't. Right? That 0 property says when your bounds are the same, the integral or the area is 0. I like that. We already said it. Slope comes from the derivative. So if I want to find the slope, let's find dy dx or y prime, same thing, whatever you want to call it. Look at my function. It has 2 terms. The sum and difference property says you can take the derivative of each term separately. What's the derivative of 2x? 2 minus, and we know how, this is our new rule. How do we take the derivative of the integral? We're going to go plug that x squared in for every t. Use parentheses. So let's see, we've got x squared cubed plus 7 times x squared. And I know I'm starting to run out of time, but don't forget the chain rule says multiply that by 2x. So the 2 was out there because that was the derivative of 2x. But then we used our new rule to take the derivative of the integral part. And I'm going to have to stop there. That's not the slope. That's the formula for the slope, right? And so if this is a formula for the slope, let's go plug our -1 in. Find the slope of our tangent. As Ansley said, opposite reciprocal. So much review in there. Most of that was review. Okay. Awesome. So thanks for being here today, folks at home. You'll get a message from me